Okay, so we have Anna and Bob running towards each other with their pipes of equal diameters. Their relative velocity is v, and let's see what happens. Well, let's also assume that the pipes are aligned, the long axis of the pipe are aligned with the direction of relative motion between them. And so if this is the situation, and if length contraction happened in the perpendicular direction relative to the relative motion, then according to Anna, Bob's pipe should have a small diameter as shown below here. So if we just basically applied sort of the length contraction concept to the perpendicular direction, then due to the relative velocity, Anna should see Bob's pipe have a smaller diameter. But remember, the situation is symmetric. So according to Bob, Anna's pipe looks like it has a smaller diameter and will fit into his pipe. So Anna thinks Bob's pipe will fit into hers, and Bob thinks Anna's pipe will fit into his. Okay, so Anna and Bob both can't be right, okay, because clearly those situations are, there's a paradox there. They can't both be right. So we conclude that length contraction perpendicular to the direction of relative motion does not occur. So the phenomenon of length contraction only applies to dimensions that are parallel to the direction of relative motion. Okay, now let's consider the relativity of simultaneity, another consequence of Einstein's postulates. For this, let's imagine again a rail car. Anna's standing in the rail car. Now imagine that this rail car has two light guns, two light sources that can put out light pulses, okay, at either end, the left and right ends, and right in the middle there's a detector which can detect the light pulses, both of them, one on each, both of them when they hit. Okay, so it can determine when they hit relative to each other. Okay, the rail car is moving to the right with velocity v, and Bob, is standing in the earth frame here at rest. Okay, so this is the situation at time equals 0. And at time equals 0, what's going to happen is that both light guns simultaneously fire. Okay? Now, at some later time, the rail car has moved to the right a little bit, and so now we see that it's displaced. Okay? But remember, the light pulse originated from here and from here. Okay, so in Anna's frame, at t prime equals 0, as I said, both light guns fire simultaneously, and sometime later both light pulses reach the detector simultaneously. And this is only true because light travels at speed c in all reference frames, even one that's moving like Anna's. Okay, so but in Bob's frame, during the time that it takes the light pulses to reach the detector in Anna's frame, the car has moved to the right, as I've shown down here. And therefore, the light pulse from the left has farther to go, because it has to come all the way from here to get to there. And the light pulse from the right has less far to go, because it only has to go from there. Only has to go to there. The obvious conclusion is that the left-hand pulse takes longer than the right-hand pulse to reach the detector. But remember, the arrival of the two pulses at the detector in Anna's frame is a single event. It takes place at a single place at a single time, and therefore it's a single event. So Bob and Anna must agree on that. They must agree on the simultaneity of the arrival. The conclusion is that the left-hand pulse must start earlier than the right-hand.